much. First of all, my name is Lorenzo Barca, but don't worry. I'm very happy to be here. I was a former EuroPLEx fellow, and I'm very grateful that I was a member of this fantastic network, and also for all the trainings that were provided. What I will talk about is the work done with my collaborators at the University of Regensburg, Gunnar Bali and Sarah Collins, and these nucleon form factors from Lattice QCD for neutrino oscillation experiments. We heard a lot of very nice talks at the Lattice conference 1 month ago, so I won't need to discuss all the motivation, but I have to do it, so please excuse me for 3-4 slides about the motivation of my work. And so, since their first prediction, I mean, neutrinos are very elusive particles. Since their first prediction in 1930 by Pauli, we learned a lot about their properties. So, for example, we know that there are 3 types or flavors of neutrinos: electron neutrino, muon neutrino, and tau neutrinos. But it took many years to discover these properties here. We know that they have a very small mass, and this allows them to oscillate or transform from one flavor, say electron neutrino, to another flavor, muon neutrino. And this quantum mechanical phenomenon could explain the so-called solar neutrino puzzle. Now, most of these discoveries have led to Nobel Prize awards, and it's a very interesting research field, and it's still very active because we learned a lot, but there is still a lot to understand about the nature of these particles. We don't know how these particles acquire their masses, whether they are Majorana or or Dirac particles, and if antineutrinos oscillate differently than neutrinos. The latter one will be addressed by the Dune experiment at Fermilab in the next generation neutrino experiment. And it's very important because it's related to fundamental cosmological questions like the matter-antimatter asymmetry in our universe. Now, I want to emphasize now why these kind of experiments or phenomenologies need some Lattice QCD input, so our work from QCD simulations. I take as an example the mini-muon experiment, a previous experiment, neutrino oscillation experiment at Fermilab. A muon neutrino was generated from the pion decay, and it was going to hit a nuclear target made of many nucleons. Naively, one can assume that many of these scattering occur, like a muon neutrino scattering of a neutron, producing muon and protons. And from theory, we know that the cross-section is proportional to the modulus squared of the nucleon matrix elements. So this is very important to remember. And there will be a nice talk, a talk tomorrow by Rajan at 9 a.m. about this neutrino-nucleon scattering, which are important. However, this is a very naive assumption because there are main challenges. First of all, let me adjust the slideshow. Yeah. There are 2 main challenges. First of all, phenomenologists like Noemi Roccos at Fermilab need a nuclear model to factorize the neutrino nuclei scattering, which is happening at the detector level, into neutrino nucleon scattering, which we know from electroweak theory. And second, the momentum transfer is in a range where excitations of the nucleons are produced. And therefore, not only n-to-n matrix elements are needed, but also n-to-delta, n-to-n star, and n-to-n pi, mainly n-to-delta, delta resonance, and n-to-n pi. Now, what we did during my PhD with my collaborator is to investigate this n-to-n pi with Lattice QCD simulations. Now, how the nucleon form factors enter? Well, the nucleon form factors parameterize the nucleon matrix elements that enter in the cross-section. And that's why we need to compute nucleon form factors from Lattice QCD for these neutrino oscillation experiments. In particular, we have weak theory, so we have weak interactions, and therefore we need axial and vector nucleon matrix elements. These nucleon matrix elements, in particular the axial nucleon matrix element, can be decomposed into the axial form factor Ga and the induced pseudoscalar form factor Gp tilde. At 0 momentum transfer, the axial form factor Ga is equivalent to the axial charge. It is very important to stress that the PCAC relation, which is a relation at the level of the operators that relates the quadridivergence of the axial vector current to the pseudoscalar current, leads to a relation that the form factors must satisfy. And therefore, when we extract these form factors, it is very important to check whether this relation is satisfied or not. And previous calculations did not satisfy this relation. So the form factors were extracted unreliably, let's say. Now, let me show you how we extract nuclear matrix elements. For some people, this is very trivial, but there are quite general people in the audience, so let me review this. We need to construct an operator O1 which has the same quantum numbers as the nucleon. So this spin and positive parity. Our operator does not only create nucleon states, but any state with the same quantum numbers as the nucleon can be created. So for example, excited nucleons and multi-particle states like NPi. The first excitation of the nucleon is the Roper 1440 MeV. And thus, we need to take this into account in our simulations. Second, we compute the nucleon three-point functions, why sometimes worse, the nucleon three-point correlation functions, this one here, where O1 bar is the creation nucleon-like operator, J is our weak current, and O1 is the annihilation nucleon operator at different momentum, P prime, P, and Q. And then we employ the spectral decomposition. Important is to keep in mind that any state with the same quantum number as the nucleon can be created. It's very important for this talk. So if we suppose that there are only these three states, but it's not true, it's just to make the argument clear, like n and star and then pi, these are the first term that decompose our three-point correlation functions. We have n to n star to n to n pi to n star to n star, and so on. And we are going after this matrix element, the nucleon matrix element, that we need for this neutrino experiment. So since the three-point correlation functions decay with the energy of our state, we can suppose that at very large t and tau, we can, the higher energy states are negligible, and so we can extract the nucleon matrix element from the ground state. But there is a problem, and the problem is that we work with statistical data, and due to the signal-to-noise ratio, large t and tau data are very noisy, and thus we use small t and tau data to extract these nucleon matrix elements. As a consequence, we have contamination from excited nucleons like n star and multi-particle states like n pi, to keep in mind. How do we extract this nucleon matrix element? A standard procedure is to construct a ratio of 3-point and 2-point correlation functions. The advantage is that the ground state contribution to this ratio here is t and tau independent analytically. So any t and tau dependence in the data for this ratio is a sign of excited state contamination. The easiest, the clearest channel is the forward limit, where q is equal to 0, and you can have p prime equal p. So nucleon operators with momentum, which can be 0 or non-zero. In particular, the expression for the ratio is simplified. We only need this ratio here. And one can extract the axial charge Ga from different channels and check whether all these channels agree or not. In particular, we also looked at the forward limit with boosted nucleon operators. So operators, nucleon operators at source and sink have equal momenta, so that Q is still 0. It's very, here, these last two channels, so when we consider temporal axial vector current and pseudoscalar current, they suffer a lot from excited state contamination, and in particular, nucleon pion states, as I will discuss briefly. Let me show you, first of all, the extraction of the axial charge from the cleanest channel, let's say, rest frame, p prime equal q equal p, which is equal to 0. So all the operators are projected to 0 momentum. This is a comparison plot between the extraction of the axial charge from local nucleon operators and smeared nucleon operators. You can see here that while the red data points show a clear time dependence, so local nucleon operators suffer from excited state contamination, the blue data points are fairly flat within the statistical precision of our, let's say, coarse ensemble for this simulation. And so the smearing has a very positive effects on the extraction of this axial charge. And we use the extraction of the value of Ga as a reference for all the other channels. But as I said, the axial charge Ga can also be extracted from boosted operators. So here we only use smeared operators, the improved operators. We consider spatial axial vector currents and temporal axial vector current. You see here that while the purple data points show a clear T and tau dependence, right? The green data points are behaving much better, and they agree within the error with the previous determination of GA. This is a clear sign of excited state contamination, so the smearing is not very effective in removing this excited state contamination. It was also observed by KHPT collaboration, so Kefei et al. We also looked at another channel, so the pseudoscalar channel. We consider a pseudoscalar current, Nucleon operators with boosted frame, so with momentum, but equal momentum. This channel is phenomenologically not interesting. However, for the n-pi contamination, it's very interesting because the Nucleon ground state contribution to this ratio is 0. So if you see any signal in the data, should be only excited states, right? Because the ground state, the Nucleon, is supposed to be 0 analytically. And indeed, we see that the data show a clear T and tau dependence, which is a sign of excited state contamination. And in particular, it's n-pi. Thanks to the work done by Oliver Baer with KHPT, we know that terms proportional to n-pi for these channel sears can be very large. In particular, at the physical point, can be up to 40% effect. So it is very important to keep in mind that n-pi states can contaminate the Nucleon correlation functions for such channels. In particular, in our work with LQCD, in leading order KHPT, we find that the correction to this n-pi states goes like a Sinch function, which describes the data pretty well. Now, phenomenologically more interesting are Nucleon correlation functions at non-zero momentum transfer because they are related, they are proportional to the form factors which are needed for neutrino oscillation experiments. From the literature, we know that the temporal axial vector current suffers a lot from excited state contamination. The data, if the Nucleon ground state were dominant or were only it is the only term in the spectral decomposition, the data should be flat, constant. There should be no time dependence. But you see there is a clear time dependence in this psychedelic plot. And this is a sign of excited state contamination. And in particular, it's due to n-pi states. Now, if the n-pi states are not taken into account carefully, the form factors GA and GP tilde are extracted unreliably. That means that the PCC relation is not fulfilled. They do violate the PCC relation. And as I said before, there could be effects up to 40% at the physical point, as predicted by Oliver Baer. And what one can do then is to compare the extraction of the form factors by considering the n-pi carefully with some KHPT-based ansatz, or by doing a traditional fit. That means by extracting the excited states from the two-point functions and take them to use them for the fit in the three-point function. That's wrong in these channels here, because it could lead to some, it is not always true that the leading terms in the two-point functions are the same as in the three-point functions. This is the main thing that one should keep in mind. Now, the takeaway message is that when the n-pi are taken into account, reliably with some KHPT-based answers, the form factors satisfy the PCC. Whereas if they are not taken into account, they violate the PCC. And the same happens for the pi-pole dominance relation. When we take into account the n-pi contamination, the n-pi states, then we get that the form factors satisfy this pi-pole dominance hypothesis. Similar approach and same observation is done by Rajan Gupta and these collaborators, PND-ME collaborations. So n-pi states are very important. Here we have done multi-state fits by taking into account n-pi contamination. So based on the work done by Rajan Gupta, Oliver Baer, and RQCD, what we did was to start a data-driven approach by using the GVP method with Nucleon and Nucleon pion operators, do the diagonalization and see whether we get the Nucleon ground state. As a pilot study, we use this ensemble with these characteristics here, where we observe some n-pi contamination. It is quite coarse, but that's why it's a pilot study. We are starting the analysis of a more physical ensemble. But this is the starting point. Now, the variational method in a nutshell. Instead of using only a single one operator for these Nucleon matrix elements and Nucleon 3-point correlation functions, one can use a large basis of operators. Now, let us suppose just, to simplify the discussion, that there are only n and n pi states in the spectral decomposition. We can find, suppose we find two operators such that 1 or 1 has very large overlap with Nucleon states and poor overlap with n pi states, and an operator O2, two-particle operator, which has very large overlap with n pi. The operator O2 must be projected to have the same quantum numbers as the Nucleon. So one has to do isospin projection and the lattice group theory. Then one computes a matrix of correlation functions of 3 quark to 3 quark, 3 quark to 5 quark, 5 quark to 3 quark, and 5 quark to 5 quark 2-point functions. And one can solve the GVP at different T0 reference times to get the generalized eigenvalues and eigenvectors V and lambda. They have amazing properties. The eigenvalues follow exponentially with the energy of your state, whereas the eigenvectors can be used to diagonalize the system. So we use the eigenvectors V alpha to construct an operator O alpha which has overlap mainly with Nucleon states. So after the rotation or the diagonalization, supposing of course that there are only n and n pi in the spectrum, which is wrong, one can construct an operator On which has very large overlap only with Nucleon states to get rid of the n pi contamination. One has to do isospin projection, as I said, and the new 3-point correlation functions must be computed. Proton to proton pi minus, proton to neutron pi 0, mediated by a big charged J minus current. We had to do lattice group theory. We have to use lattice group theory to do the lattice irre projection, which was done some years ago already in n-pi scattering studies in the Roper channel by Leskovec, Prelovsek et al. But we also look at a boosted frame, so operators with non-zero momentum, which are important for this, for our studies. And after doing the weak contractions, in the case of the proton to proton pi minus, these are the topologies. So we have diagrams which we call A-like, B-like, C-like, and D-like. The most important one is this D-like diagram. It's very important because it has the largest amplitude, so it contributes a lot to the full 3-point function. And it follows, it's easy to see that it follows the leading order catch-PT prediction. And only this diagram here explains the largest n-pi contamination that we see in the standard Nucleon 3-point function. We also compute Nucleon pi on 2-point functions, of course, for the GVP. And it was interesting to see that diagrams A and D decay with some n-pi interacting energy, whereas diagrams B and C decay with the Nucleon energy. And this was anticipated by K-Fei some years ago, and I would like to thank him for discussion at the Lattice conference about this matter. And then finally, we use the 2-point functions to solve the GVP, and these are the results of the GVP at 0 momentum. What we observe is that the first eigenvalue follows with an energy of the Nucleon, so the ground state. The second eigenvalue has an energy very close to the n-pi or n-pi-pi non-interacting energy. And the eigenvectors behave very nicely in the sense they are constant, fairly constant with time. This is at 0 momentum. We solve the GVP also at non-zero momentum. And here it's very clear that the second eigenvalue has an energy which is very close to the n-pi non-interacting energy. And so we can use the eigenvalues, and in particular the eigenvectors, to do this diagonalization. As a first plot, let me show you the pseudoscalar channel. Again, we don't work with O1 or O2, but with a diagonalized operator On, which takes into account these eigenvectors to do the diagonalization. And we construct a very similar ratio of 3-point correlation functions, more sophisticated. Remember that the ground state was supposed to be 0. And after the diagonalization, we get, for this GVP ratio, so using GVP improved operators, results which are consistent to 0. Whereas the standard ratio with, smeared only Nucleon operators, we had non-zero results. And the conclusion is that the GVP method removes completely the n-pi contamination in this channel here. So it's very impressive that this works very well in this case here. And it works also very well in the temporal axial vector current. In this case, the ratio should be proportional to the axial charge. But the blue data points are quite far off from the reference values which suffered less from n-pi contamination. But after the GVP projection, then we get results which are consistent within the error at different sourcing separation, even at 0.6 Fermi, with the previous determination of GA, which is very surprising. Phenomenologically more interesting, of course, are Nucleon form factor and non-zero momentum transfer, as I said. Thank you. And in particular, what we see is that the GVP, even in this case here of non-zero momentum transfer, works very well, because now the data from the blue data points, which are computed from the standard ratio using unimproved operators, now the data are shifted close to this green band, which we suppose to be the Nucleon ground state, and in particular at the source. But you see that at the sink, there is still some trace of contamination left. Remember, we use only Nucleon pion operators with relative unit momenta. We do not include in the GVP n-pi-pi, S-wave, or n-pi with relative high momenta, which are also important and can contribute to a few percent, which is missing in this picture here. And the same happens for the other channels, say A4 and spatial current. So everything looks consistent with current perturbation theory, but there is some trace of contamination left at the sink. Now the question is, one remark is that now we can only need a very simple fit to extract the form factors, a constant fit plus some exponential which takes into account what is missing here to extract the form factors. And we can check whether they satisfy the PCC relation. What we find is that the PCC relation is satisfied up to discretization effects, which must be taken into account. And in particular, we compare different methods, and we find consistency between all the different methods. So GVP improved the correlation functions with a simple fit, and unimproved Nucleon correlation functions with some KHPT inspired fits. And they all give results consistent, and the PCC and PPD are fulfilled up to some discretization effects. And let me take the conclusions. Structure of nucleons and excited nucleons is relevant for neutrino experiments. The variational method with n and n-pi-like operators works extremely well in the forward limit. It works well also in the off-forward limit to extract these matrix elements. Please note that we do not consider n-pi with higher relative momenta, but only unit momenta, which according to KHPT gives rise to the largest contamination, if of course the momentum transfer is unit. And we also need to include n-pi-pi operators to achieve even better results. This project confirms the kind of perturbation theory picture of n-pi contamination in some channels. And I was very happy to see that the Lattice conference, new similar projects are starting and making good progress on this with n-pi and even n-pi-pi operators. So, and finally, what is next? We want to finish to write a more detailed paper because so far we have written just a letter. We want to include many details on this study. We want to compute n-to-n pi on this ensemble. We have the data. We just need to understand how we can decompose the matrix element. At the moment, I don't know this decomposition. I have to work out. We have to work out. We want to include more physical ensemble at the physical limit. And finally, we want to also study n-to-delta matrix elements and n-to-n star, which are important for this neutrino experiment. In particular for Dune, which will start taking data in roughly approximately 5 years, if I'm not mistaken. There was a very nice talk by Noemi Rocco at the Lattice conference, plenary talk, theory needs of neutrino experiments. And we are planning to have a Lattice QCD session, to organize a workshop about neutrino nuclei scattering for next year, and to have a Lattice QCD session related to this topic here. Finally, what I discussed was based on these papers here, plus one in preparation. I would like to acknowledge all the people with whom I have interacted and for all the useful discussions, and also all the people who gave me offer me a research stay, and in particular to the network, EuroPLEx, Francesco Di Renzo, Petros, and everyone, for all the trainings that was offered. So thank you very much.